All right, I think we're live. Hello, everyone. Thank you for joining our workshop. This is I think this is our sixth or seventh workshop for our summer hackathon, and today I am joined by Alex from Mysten Labs, and the topic that this workshop is going to cover is going to be on Sui transaction blocks. All right, so yeah, thank you, Alex. Is your turn?
Thank you, Henry. Hello, everybody. Good evening, good afternoon, good morning. I'm Alex. I'm in the solutions engineering team. And today I will talk about some parts of programmable transaction blocks, what they are, and some things to avoid, some things to do, and best practices. This will be a technical workshop where I will do some live coding. It will be all about analyzing code. It will be mostly in TypeScript because that's the main SDK that we support, but everything can be applied to any other SDK. So let's start with programmable transaction blocks. So before having programmable transaction block, we had a command like an RPC command for everything that you could do with Sui. There was a command for pay Sui, a command for pay all Sui, a command for transfer, and the commands kept growing exponentially, and it was a non-sustainable road that we were on. So we introduced programmable transaction block, which the main idea shown here is we have 5 commands. We have inputs, commands, and results. So this programmable transaction block knows all your inputs that you're using that you want to use. So we have one big array that's full of inputs, whether that may be a pure input or an object input. Pure input is everything that it's native to move. That would be like unsigned integers or addresses or booleans. And objects are any Sui or move object. So these are the inputs. Then you have 5 or 6 commands that you can use on the inputs. These commands are move call, merge coins, split coins, transfer objects, upgrade as for a package, publish again for a package, and make move vector, which is a helper. So you can combine all these commands, have them work on the input, and these commands produces results. Results is again a big array which stores as nested result the output of each command. So if I make a move call on input 0, I will get the result, nested result 0. If this move call returns something in here, they will know that we have something. If move call doesn't return something, again, we have a nested result, but at the end, it won't have anything. Merge coins as well. Merge coins here that never returns, but it takes one input in the beginning. It should always be a coin, any coin. And then it takes an array of other coins that they will be merged into the first. Split coins takes one coin and as inputs takes pure values of U64 that will output a result, which will be the coins that were split from the initial coin. Transfer objects takes an array and a pure address, and it will transfer all the objects. Here I said like result. Notice that I said result 00, which means in the results array, go to the first result and the first object, because in a nested result, the move call may return one or more objects. So we can take the first, the second, whichever we want. That's why, so results is a nested array. It's an array of arrays that come from split coins again, would be many, in most cases it will have many results, many coins. Upgrade and publish is used for package, upgrading the package and publishing the package. Make move vector is the helper command that is used in order to create a move vector. Because that is, we needed that helper method because it's quite difficult for the TypeScript to make it by itself or any other SDK. So one thing to keep in mind is that all of these are stored in bytes, so nothing has run yet. You say I will have one input, an object, an input, an address, and you do a move call on the object and then transfer the result to the address. Nothing has happened yet until we execute the transaction. So in the programmable transaction block, we store everything that should happen on chain. And because we can mix all of this, we can do many move calls in a single programmable transaction block. We can do many transfers, splits, merges. It allows us to batch many commands, and it allows for composability. That is why, in order to have an easier time when developing on Sui, it's a very good idea to keep in mind how programmable transactions work when we write move code. And I will go to the code now and write the code in such a way that will allow us to leverage the power of programmable transaction. So I have over here, let me maybe share the repo. The repo is this one. So it's in my private repo. I have the examples that we are going to see today. I have some simple move code. It's kept very simple in order to be able to understand what's happening easily and focus on the programmable transaction. And we have some scripts. We have some examples of programmable transactions that have some suggested practices and some things, anti-patterns that people should avoid. Let's check the move code really fast in order to see what we are going to do. So this is a very simple module that defines an NFT structure. It has only color, weight, and text. Color is a string, text is a vector you wait. I made this on purpose in order to show you how we deal with this on the programmable transaction block side. We have some correct patterns. This is a min function. This is just means these types of NFTs. It accepts a color, it accepts a weight, and it puts the same text every time, and it returns the NFT. Here, the important point to note is that we return the NFT. So we create it and we return it. And as we will see in the next anti-pattern, we don't do the transfer part. So in the old days of Sui, maybe it would make sense when you mean something to also transfer it to someone. Maybe add a recipient over here. And then you could, every time, here I'm just transferring to the color. And then every time transfer the object to the recipient. Now that we have programmable transaction block, this pattern is an anti-pattern and should be used in very, very special cases. In most of the times, it's the best way to go about it is to just return anything, any object that you have, and then transfer it using the transfer objects command of the programmable transaction. So as we will see, in the programmable transaction, we will first do a move call towards mint, and then we will get the NFT as a result, and we will transfer it to whomever we want. Another pattern that we will see here, we have a cost limit. That means that it has a fee. The fee here is just transferred back to the sender. This is not something that will happen in a production code, but this is just for the sake of simplicity. But the important point over here is this assertion. So in the old days, where there was this debate whether a move programmer should accept a coin of larger value than it needs. So whether this coin, so if we have like a fee, the price over here is a constant. It's like 100,000 Mysten for this NFT. The question is whether we should accept coins larger than 100,000. Now that we have a programmable transaction, the answer is straightforward. It's no, never. We always assert a good move program will always assert that the value of the coin provided is equal to the price that we want, is equal to the one that we want. It should never be bigger and then we return the change. Because with programmable transactions, we can always split the coin in the previous command, get the value that we want exactly, and then that passes that into the move vector. This way, the code is cleaner. What happens is like more visible, and people don't have to worry that the move contract might get more money than it should or try to steal. So here again, I'm returning directly the NFT. We have some setters that allows us to change the color of the NFT, to change the weight, or to change the text. And I have a single getter that allows us from another module to read the color. Keep in mind, even though this returns a string, programmable transactions right now, as we will see, can't read returns. So you can never read this color, the value of this color, whatever it may be, in a programmable transaction. The way you go about it on the backend is that you get the object directly and you read the object on chain instead of doing a call that costs gas. Reading is free. And this is just best practice. It's a good idea to always have a function that allows us to burn. Without this function, the NFT would remain on chain forever, no possibility to burn it and to get the rebate back. And the next move module has a locker. The locker is just a simple struct that has only the UID. It is a shared object. I'm sharing it. It's shared when it was shared when the contract was published. I published it just before this presentation, so it's already on chain. And the functions that we can do with the locker is we can lock an item inside, which means, and because I don't have any function that allows us to take the object back, the object will remain always under the locker. It's using dynamic object fields. So I can lock an item inside, any type of item, as long as it has key and store. I will be locking the NFTs that I will be minting. We can borrow an item, and this is how it should be done in these cases. This is another thing that to keep in mind. We can borrow it, we can return it, and we can use a move thing that is called a hot potato. The hot potato, in this case, I call it must destroy this. It has no abilities, no drop, no copy, no store. So you have to do something with this. If in your programmable transaction don't deal with this, it will always fail. So then I have the return item that it's the only way to destroy the hot potato. I'm destroying it over here. The hot potato keeps the ID of the item as data. So when you're returning, there's a check that the item that you're returning is actually the one that you took, and you're not returning another item. And then I put it back inside the locker. And we will talk also about a small pain point of PDBs. That is, PDBs cannot work with references. So whenever you're returning a reference, as we will see, PDBs will fail to use that in a subsequent command. This is why we need this pattern. Whenever you need, instead of working with references, we actually return the whole item. So this is for the move part. We will also see how mass meeting is done correctly. How can you link calls, the hot potatoes that I was talking, and I will have an example of offline signing that is a requirement, a very frequent requirement from many partners. Offline signing, so whenever we do a programmable transaction, we need to get the data of the object, the reference of the object. We'll talk about it from chain. If so, it needs a provider and it makes some calls toward the chain before executing. If you want to avoid all these calls over the chain, you have to structure your programmable transaction block in a different manner and you have to provide more data. We'll see how that is done. In interest of time, we could have, there's another topic that it will be added in the future in this repo, and that is how we make sponsor transactions. We can do sponsor transactions where the owner of the objects that are going to be used in the transaction is signing the transaction, and another person, another address is going to provide the gas object and is going to sign the transaction as well. This thing was not included, but it will be in the near future. So let's dive into the code. I will start with a new file. Let's see. So the first step that we should do whenever we deal with programmable transaction is download our library. That's at Mysten Sui.js. I have already downloaded. Our package JSON looks like this. I have the at Mysten Sui.js. I have the noble hashes. This is a hash is needed when signing offline. Sometimes you can use a key pair, but I prefer this. And I use the .temp in order to hide the private key. Imports. So the first thing transaction block that we should import always is the transaction block. So assuming programmable transaction blocks always work in correlation to the move code, I have to see the function that I'm going to call. I have to know what objects what arguments it takes and what it returns in order to be able to work with it. Right now, I just want to call mint. In order to do that from a programmable transaction, let's make a new function. It should be async. So the first line usually is always this one. Const dx is a new programmable transaction block. So programmable transaction block has, here's the making back, has we can see all the functions that we can call, the split coins, the publish, the merge coins, make move vector, the move call. These are the main commands that we can use. Block data will show us the transaction as is at that point. Get digest is getting a digest of the transaction, that the resulting transaction. Object, we will use it in order to assign a new input. Pure as well. Serialize is used in order to make the programmable transaction into BCS bytes. Set expiration if you want, set gas, budget if you want. Most of these things are done automatically in case of TypeScript SDK, but in other SDKs you might need to do it. But these are needed. Set gas owner if it's a sponsor transaction. Set gas payment, here we set which coins we want to use. In most cases, if we don't set it, the TypeScript SDK will choose as many coins as necessary. Keep in mind over here that in a programmable transaction block, whenever we set gas payment, so any coins that go into for gas, we can set more than one, an array. The limit is 256. Sorry. 256 coins. They will be smashed down and merged into the first. So a programmable transaction may fail. That means that if it fails even on the last command, all the previous commands will fail as well. Nothing will happen on chain. They are atomic in that sense. The only exception is that the gas payment, whatever we set or it was chosen for us as gas payment, that will be merged into the first coin, and that will happen every time, even if it fails. Where were we? Set gas price. This is also chosen for us. Right now, it doesn't have much of an effect. It should be the reference gas price of the chain that you're using. Even if you put more, it won't change anything. In the future, you will be able to pay more. And when that functionality is available, you will also be able to make your transaction go a bit to have priority, especially if it involves consensus. Once not all transactions go to consensus. The ones that we will see today, most of them won't. The ones that involve the locker, which is a shared object, and all transactions that involve shared object, those have to go through consensus. Set sender is the one that it's initiating the transaction. This should be an address. And shared object reference. This is for shared objects, split coins, transfer objects, and upgrade. Yeah. These are the things that we can do. Right now, I want to make a move call. I want to call me. Move call takes 3 arguments. It takes 1 argument. It takes an object that has 3. It needs at least 1 field. One is the target, and the other is the arguments. And optionally, if it's needed, type arguments. We will see about this. So the target every time is on chain our function. So on chain, sorry. Here's the explorer. I have shared this object in this transaction. So on chain, I published this package. This is a package that we were seeing. It has the locker and the NFT, and the package is this. So the definition of the function that we want to call in order for the move VM, in order to be able to read it. Here I will write it explicitly. I have it in the M file already, just for clarity purposes. I know that the module is NFT, and I know that the function is mint. So this is the function that I want to call. The function needs color, weight, color and weight. It needs a string and a U32. So I will again write it explicitly. Let color equals tx pure. This is a string. Let's say it's blue. And so tx pure takes 2 arguments. First is the data that we want to the primitive that the chain understands, and on the next is its type. In this case, it's string. Let's talk about this for a moment. So string is not a primitive for move. String is an object, and usually for that we would have to create that object first. The TypeScript SDK does this for us. So whenever we say string, because it has the data already, it has the BCS is loaded, and it's with the definition of string, then it does it automatically for us, and it's considered, and it's the pure. This might be a bit of a disambiguation or not really straightforward, because string is not a pure. It's not a primitive. But programmable transaction blocks of the TypeScript SDK allows us to do this. So whenever I say tx pure, the inputs array that we talked about of the programmable transaction gets filled. So right now our input number 0 will be this. And then I want the weight. let's say, it's always a good idea to use only strings, even if it's a number. Let's say it's 50. Even if it's numbers, it's always a good idea to use strings. Anyways, all this data has to be serialized in BCS, binary canonical serialization. The all SDKs will do that for you. TypeScript SDK works with strings, and it's a very good idea because for very long numbers, the JavaScript in general behaves a bit weird, and you might get some weird results if you're not careful. So either use big int or just strings, even if it has to do with a number, and then just give the type u32. Now this will be made. This will be serialized as the u32, and the MoveVM will know it's an integer. Again, this is our input number 1 in the input array. And now we declare the command number 0. We'll take arguments color, we'll take arguments weight. The last argument is the TX context. This argument is something that will be provided by the chain. We never have to provide it. We cannot provide it. We don't have any ways to create a TX context. And we don't need any type arguments. The type arguments in any function are shown here. Let me show you a quick example. Over here, this denotes that we need a type argument. But in our case, the main function has no type arguments. The move call is returning something. It returns an NFT. If I execute a transaction right now, so let me import. Sorry. In order to execute the transaction, we need a signer. I have made a utility. This utility is getting me the signer. Where is it? Inside util. So get exec stuff takes the private key from the env. Sorry. And it creates the key pair, it gets the address, it gets a provider and a signer. In this case, I will also need to add this part. Now, if you try to execute this transaction, we need a signer. Transaction block is the TX. Request type. Request type. We have two request type. Wait for effect cert. This means that you get the certificate. The validators accepted the transaction and they are going to execute it. This does not wait for execution. Is the fastest of the one, but maybe the state, by the time you get a response, maybe the state in the full node is not updated. Wait for local execution means that the state in the full node is updated, and you can get some more. This works with some options. You can get the effects or the events of the programmable transaction block. If I try to execute it right now, let's see our result. This will not work because I'm copying an NFT and I'm not doing anything with it. So it says we get an error, which might not be really straightforward. We are working at that as a team, but it says that I have a result that I didn't do anything with it. So right now I have to call transfer objects. I have to take the NFT and give it to an address. In this case, I will do it to the same address as the signer. Now, if we try to execute this transaction, it will go through, but I didn't await. So we didn't get any result. Let's execute it again. I have a digest. We can go check it. Success. The transactions was a move call, and then the transfer of the result of the first command, which is the move call. Our inputs was one pure input that was a string, a pure input 2, and an address. I didn't talk about that. Here I had all my inputs, but we can use the inputs directly when we need them. Whenever we call tx pure or tx object, the inputs array will grow by 1. And if I check this is the NFT that was created, and I am the owner. Now, let's go through the rest of the functions. And the examples that I have. The mint is the one that we just wrote. I just set the sender every time. Set sender means whoever is the one that is calling. The NFT, here I do a console log NFT. So let's check this transaction. Let's call it. Here I did some messy coding in order to be able to call one by one. Let's call mint. The important part is this. So kind result index 0. So the mint function, I'm doing a console log NFT, and we have heard in our department this question: why don't I get the data of the NFT? So why don't I see the color? Why don't I see the weight, its ID? When I do the console log, the transaction has not executed yet. So nothing has happened on chain. So we don't even know. What we know is that since we did a move command, the results array that it's under the hood of the programmable transaction block has increased by 1. And it says over here that the result has at index 0 a new entry. And this is how we decipher this console log. But keep in mind that everything that we say should happen happens only after we execute the transaction. Mint with exact payment. So this is another pattern. Whenever we have to pay, it doesn't have to be a mint. Whenever we have to give a coin as payment in a function, we always, as I said, assert that the payment that we get is exactly the same value that we need. In this case, we know from the move contract that we want 100,000 Myst. The values are always in the decimals. So in case of SWI, it will be Myst. I'm creating a transaction block, and the fee, I say TX gas. TX gas means the gas coin. So we can take directly, this is only for SWI payments, of course. We can split directly the gas object. So from the gas coins, the gas will be deducted, but in this programmable transaction, a new coin will be created that will have value or balance the payment that we need, the 100,000 Mysten. And then after the split coins is done, we call the move call the cost limit that needs a fee, and we give it as an argument. If you remember the cost limit over here accepts as argument only a fee, and it gives us a ready-made NFT. Let me delete this. And lastly, because the function is returning the NFT, we transfer it to whichever others we want. Then we execute. Mint and change. So we have in the NFT function a few setters. So we can change the color, we can change the weight, we can change the text. Let's see how we can combine many move calls into one in a single transaction block. I define the transaction block. I set the sender as myself. This is optional in this case, but I like to do it in case it's a sponsored transaction where it's mandatory. We create the NFT by calling mint. So I call first mint. I give the arguments, the color, and the weight. The color and the weight, in case you're wondering, the color and the weight is given inside as arguments over here to the function. I take the NFT that is minted, and I want to change the color to purple. I will call the move call the change color in a move call. I will give the NFT that I got as a return from the previous transaction, and call it with the necessary arguments, that is the NFT and the new color. Then I will change the weight. I will call again the change weight. I will get the same NFT because these functions don't return, change weight and change color don't return. I will give the arguments, and it will be executed in the same transaction block. And the same with text. Change in one transaction. This is a new text that I want to put inside the NFT. I call the change text. I give as arguments the NFT and the new text that I want. And finally, I transfer the NFT to the address that I want. Let's run this function in order to see it. And change, here it is. So let me take the digest and let's watch it on the Explorer where it's easier to see. So I do 4 move calls and a transfer object. The result is this NFT. That now has color purple, the new weight, and the text, because I set it as a vector U8. It comes out as a vector U8, so we cannot read it. I have 5 inputs: the address that I sent to, the text that I made, the color, the initial color, and the initial weight. And this is the main way to link many transactions. The limits over here are, we can have up to 1024 commands. So I can do like 1023 move calls and 1 transfer. I can do 1 split, 1 merge, and 1022 transfers. Whatever suits me. The total number of the commands has to be 1024. Otherwise, we will get an error that limit exceeded. Also, another limit that we have is the number of objects inside the transaction. So the objects inside programmable transaction block, either resulting or inputted, should be up to 2048. The pure can be as many as needed. there's no limit on how many pure inputs we can have. So this is a bad call. I'm calling the Mysten transfer, and I'm trying to transfer the object afterwards, but because the object is transferred, this will not work. Let's watch it once. What kind of error I will get. So here we get invalid result RT the same. It says that you're trying to transfer something that it doesn't exist because it's not returned. The way to correct it is to not try and transfer anything, just do the move call. Now, this should be a success. It is a success. If we check the events, everything was transferred. So what's the problem with doing it this way? The problem doing this way is that I cannot link new commands. So this programmable transaction has to stop here because I cannot use the NFT. So there's no NFT returned over here and I cannot use it. This means that if I wanted to change the next transaction, the color, I have to wait for it. So the problem is time. I have to wait for it to execute to make sure that it executed. And when it executed, I have to parse the response. This response, I have to parse it and to find the object that was created, get the ID, and then do another totally new transaction block. This will take time, and if there are done many in very fast, then the full node might even rate limit you for spamming it. Also, you will pay slightly more gas for this. From all angles, it's not a good idea to transfer inside a move call. You should always return, and then in order to be able to use the return in many commands. Let's go to mass minting. The intuitive way to do a mass minting, let's say I want to mint 100 NFTs that are gray and weight 11, is to get the addresses. Here I'm filling the same address 100 times, but let's say that I want to airdrop to 100 different addresses the NFTs. I will do one transaction block for each address. In the transaction block, I will create the NFT and then transfer it. This is an anti-pattern because this can be done in a single transaction block. Here we make 100 transaction block, and if I use the public full node, this will limit me for sure. I won't even try to call it. The correct pattern and the correct way of doing mass mint is, again, I want to mint 100 gray and with weight 11 NFTs. I have 100 addresses that I want to airdrop them. I do one transaction, and then I loop over the move call and the transfer. So I do 100 move calls. I call 100 times. So for each address, I call once the mint. I get the NFT. I transfer it to that address. Then I mint the next one and transfer it to that address. And this happens all in a single transaction block. And we can even try to call it over here. This will take a bit longer. So notice that in this case, I didn't request anything to be returned. In order to, if you want to see data in the return, you have to use the options and you have the show balance changes, how much SWI was lost or gained, the effects of the transactions, any events that maybe the move call is emitting, the inputs that were used, and the object that were changed can be used, any that we like. In this case, because the result would be pretty big, sorry, I decided to have the return clean. Sorry. Okay. Let's check the transaction. So I have 200 commands, 100 move calls, 100 transfers. I have created 100 NFTs, and in this case, I transfer them all to myself. These are the main patterns for when returning and how to do a mint. Let's go to the locker. Here we will call the lock function that locks an item inside the locker. This is a shared object that we have, as we've seen in the code initially. Then, in order to change something, I will call the borrow item. The borrow item, if we remember, returns the item and a hot potato that must be resolved in the same transaction. So I'm calling the borrow item. I get a nested result that has two items inside. The first item will be the NFT. So I'm changing the color of the first item that I'm getting. I'm changing the weight of the first item that I'm getting. I'm changing the text as well. And then I call return item. The return item is the one that deals with the hot potato that I have. If I don't call it, then the function will fail. If I try to transfer it or do anything else, the function will fail. And again, I give the NFT, I give the hot potato as well, and I need the locker as well. The locker here, this is an ID, the locker ID, which I have it in my environment. Here I inserted this is the way. So TX object will add it in the inputs, and the programmable transaction block will know it's an object. And then I execute the transaction. I have a failed transaction. In this failed transaction, I'm trying to borrow it and immediately transfer it to another address. This will fail because in here we have two results, two objects are returned. One we are sending it, but the other we are doing nothing with it. You can play with this. And you'll see there is no way around it. You have to call the return item. And here's the example. So in the locker move, I have the anti-pattern where I return the reference to the item. But today, programmable transactions don't work with references, so I can get a reference, but this move call will fail where I try to change the color. So let's get an item ID. Here, many were created. Let's take one. And let's log, firstly, let's log the item. Confirm local execution false. Why? Over here, I'm just waiting for the effects. This means that the transaction is final. I have finality, but it may not have executed on the full node. Of course, and the time that usually needs for the full node to execute, it's about 3 seconds or 1 to 2 seconds actually until the next checkpoint that has my transaction here has already executed. So the locker was changed. I call the lock. If we go inside the locker, we'll see we have two. This is from my test earlier. And this is the new item that was locked. Have it as a dynamic field. We can watch it. It's an NFT of color silver and weight 88. We can see it over here as well. So now the item is the item is inside the locker, we can see that this is the ID of the item. Let's try to change the item. So now we will call the borrow and then the return. I get a huge response because I'm calling many calls inside one transaction. Check it over here. I'm doing move calls, I'm doing the borrow item, then I'm changing the color. The color of the NFT right now should have changed to metallic green, the one that I said, and the weight should have changed as well. I'm calling the change weight, change text, and finally, I'm calling the return item. All in one single transaction. This is the pattern whenever you have to deal with the references on programmable transaction and move. You should return the whole item. You can use a hot potato in order to make sure that the item was returned or transferred wherever you need it. And I will also mention this. You can test the reference borrow or the fail borrow yourselves and see what errors you will get. The reference is not working. I will mention this for that has to do with move. Over here, we are returning the item inside the locker. Let's say that we wanted to give it to a certain address. Over here, it's the only place, and I read it in the comments, that it might make sense. So let's say that I don't want it to put back in the locker, I want to transfer it. It's the only way, the only place that it makes sense to use transfer instead of returning the item. Because over here, I want to make sure that it goes to a specific address. I log the item and only one guy can get it back. So if I return it, I give the opportunity to be sent anywhere. But in this case, it makes really sense. Sorry, I have to charge my PC. In this case, it makes sense to use the public transfer. So please go through the code. Let me show you this is the repo that has the whole code. Try it, test it. Any questions you have, you can ask it in the TG Tsunami Riders on Discord. Our team will try to help you. Try to use these best practices in order to have cheaper and faster programs on Swing. Thank you.
Hello, hey. Thank you for that workshop. All right, let's see if we have any questions. All right, it seems like there was one question about that wasn't related to this topic. It was more of a general question on how do Sway smart contracts interact with the front end, and the answer to that is we usually do that through SDKs, such as the TypeScript SDK or the Rust SDK. And like we did introduce as a part of this workshop, we did kind of introduce how to use some of them. And there was also one other workshop that we did, I think last week, that was more specifically about how to use the Sway TypeScript SDK. And I also put the link for that in the comments. So yeah, if you guys are more curious about that, please check it out too. I think for now, I don't see any other questions.
So for this question,
you,
I can help.
Yeah.
I can help a bit. So if you want to write so if you want to do transactions, the way you do it is with programmable transaction block. That is how the front end actually makes move calls towards the towards Sui. But if you want to read, then you use the provider, especially with types of SDK. You can provider holds all the read, get that, get all coins, get balance. All the read functions are inside the provider. That's it.
All right, cool. All right, I don't see any other questions. So yeah, thank you again, Alex, for this great workshop. And please stay tuned. I think we have a few more coming up this week. Yeah, thank you guys for like joining, and see you guys next time.
Thank you for having me. Good luck,
Bye.
everyone.
Yeah.
Bye bye.